Thank you. Thank you. Let me make just one step back, because a couple of people asked me about something which possibly didn't explain so well. Let me recall one thing. So Loss-Milan defined is CD K-infinity business through convexity properties of the relative entropy in metric measure spaces. And now we were trying to, those spaces included Finsler manifolds, and we were trying to sort of remove this Finsler stuff out. And the idea is to enforce the condition that the Sobolev space W12, whose definition we have seen yesterday, is Hilbert. Now, what this has to do with heat flow, this was a sort of three-step program. Begins with the observation that W12 is Hilbert if and only if the L2 gradient flow of the Dirichlet energy is linear. And then it passes through the proof that the L2 gradient flow of the Dirichlet energy coincides with the W2 gradient flow of the relative entropy. And finally, with the observation that the gradient flow of the relative entropy is stable. Now, what I've shown you, not really the proofs, but details of the proof, is that this guy is indeed stable. This passes through this gamma Riemann inequality for these slopes. I mentioned you this result of myself, Covada, Ambrosio, and Savare concerning the identification of these two gradient flows, but I never really, underlined anything about the first point, which creates some confusion. But in fact, the first point is easy. So maybe the missing observation is that so if we have, even in a metric measure space, if we have our energy functional, which is 1/2 integral of minimal weak upper gradient squared, plus infinity if your function is not Sobolev, then asking for W12 to be Hilbert is the same as asking that this function is a quadratic form, which means that it satisfies the parallelogram rule. Okay, so this is equivalent. So this is equivalent to W12 is Hilbert. Okay? For every f and g. And now you can check, that's an easy algebra exercise, that if this holds, then the subdifferential of this function is linear. It linearly depends on the function. So this implies the subdifferential is linear in f. So it contains a unique element for every f which this guy is not empty, and this element linearly depends on f. So that then the gradient flow equation dtf equal minus the gradient or the subdifferential in f must be linear. Okay? And conversely, actually, also the converse implication. And this is more an exercise, if you want, in algebra than in analysis. Imagine you have a function on a finite dimensional Hilbert space, so Rn. Then what I'm saying is that this function is a quadratic form if and only if its gradient is linear, which is pretty much in finite dimension and triviality. In infinite dimension, you just have to care a bit about some continuity issues, but that's all. Okay. So that's why I can either speak about linearity of the heat flow or Hilbert property of the space W12. Now, having said this, let me come back now to our business about RCD K-infinity spaces. And so I want to convince you that on spaces, on CD K-infinity spaces, where W12 is Hilbert, the gradient flow of the relative entropy has some additional information, which additional property which doesn't have in the Finsler case. And so I need to. So the first thing that we need to do is to introduce another notion of gradient flow for convex functions on metric spaces, which is different from the one we have already seen. This is the EVIK notion, and so this is a computation that I showed you already yesterday. So take a gradient flow, so in the standard, so everything is smooth, we are on RD, and compute these two derivatives. The first derivative is, well, I fix a reference point, and I differentiate in time the square distance. And I get a result. And the second derivative is okay, I interpolate from my xt to my reference point along a geodesic, and I differentiate the energy. And the result is the same. So I can plug these two informations together, and using the convexity or K-convexity of the energy to deduce that the derivative of the distance squared 1/2 is bounded by this quantity. which is something which makes sense on a metric setting. So as usual, I take this as a definition. And this is my EVIK gradient flow. So I just replace x minus y squared by distance squared with x and y. And recall the result by Savary, which grants that if a curve is a gradient flow in this EVIK sense, then it is a gradient flow in the other sense. So this is a non-trivial result, but it grants a little bit of compatibility within these two notions. The vice versa is not true. Okay, so now I want to convince you that on RCD infinity spaces, the gradient flow of the relative entropy is an EVIK gradient flow. Okay. So what do I need to do? I need to take a heat flow, a reference measure, and compute these two derivatives, right? I mean, that's basically what we have to do. If we prove that these two derivatives are the same, essentially we're done, right? This is easy to compute. This is very tricky, and if you learn how to take this derivative, you learn quite a lot about analysis in metric measure spaces. So let's start the first. The first is pretty easy. It's just I can use the duality formula in optimal transport program. So I fix a time t, where the distance squared is differentiable. There's plenty of those because the distance squared is an absolutely continuous curve, as an absolutely continuous function, as a function from R to R. So it's almost everywhere differentiable. So fix t 0, and now find the counter-Abresch potential from mu t 0 and your reference measure nu. And then one half the distance squared is going to be equal to the maximum of the dual program, right? Well, for every other time, the squared of Arcadian distance is greater or equal than the same quantity. Okay. Now that's nice because when I take the difference, the part with my reference measure and my phi c disappear, and I only remain with the derivative of the squared of Arcadian distance is the same as the derivative of this integral, right? Which now there is just the counter-Abresch potential and there is this mu t. But mu t was a measure with a density, rho t, and the derivative of rho t was, at the heat flow, right? So that was the Laplacian. So that's done. Okay. So that's easy. What should be? Now the derivative of the entropy is much more tricky, and I need a couple of informations before attempting to differentiate the derivative of the entropy along a geodesic. The first information is a regularity information due to Tapio-Rayala, which does the following. I'm stating everything in the compact case. It's not really needed, but simplify the statement. Take on a CD K-infinity space, take two probability measures with bounded density, and say that the space is compact. Now, what Rayala tells us is that there exists a geodesic mu t along which the entropy is K-convex, and which is made of measures with uniformly bounded densities. Okay, so typically the CD K-infinity condition just grant the existence of a geodesic where the entropy is convex. Right? But a priori entropy convex, you can still have some small region where the density, say, grows quite a lot. The entropy can be finite even with a very high density in some place. And Rayala tells us, okay, this can happen, but for sure there will be geodesics where this does not. Okay, so you can appropriately choose a geodesic such that this is not the case. Another theorem in this direction is a metric version of the Brownian theorem or Brownian-Mecan theorem, which does the following. So assume you have a geodesic such like the one provided by Rayala's theorem. So assume you have a geodesic with a uniform bound on density, and take a lifting of it. So what is a lifting of a geodesic? So this plan, this is a measure in the probability measure in the space of continuous curves, such that Et push forward pi is equal to mu t for every time. And moreover, the integral, the total kinetic energy, so if you want the integral, pi should be concentrated on geodesics, and the integral of gamma t dot squared from 0 to 1 dt integrated with respect to d pi this should be equal to the square root of Arstein distance between mu0 and mu1. So essentially, what is this pi? This pi, I mean, is following, if you want, the path that each atom, you can imagine a versatile geodesic as I have a mass, initial mass mu0, which is moving, and is reaching a final mass mu1. And well, in this point of view, I can imagine that every atom is moving along a single geodesic in such a way that the total path will be an optimal plan from mu0 to mu1. And this plan pi is describing the path that every atom is doing. Okay? In this smooth case, this plan pi would be of the following kind. Would be t push forward mu0, where t of x would be the curve which at time t is equal to exp of minus t grad phi x. So the McCann theorem tells us how geodesics on manifolds are made. You have a Kantorovich potential phi, and now every point starts moving from x, goes in the direction minus grad phi. So at time t sits at x of minus t grad phi x. Okay? And now this metric Brownian theorem tells that in some sense at the first order, this is true even in the metric measure setting. What does this mean? It means that the plan pi represents the gradient of minus the Kantorovich potential. So you remember that yesterday I gave the definition of what it means that the plan pi represents the gradient of a Kantorovich of a function, and now this is what happens. So morally speaking, this theorem tells that for curves in the support of pi, if gamma is a support of pi, then gamma prime at 0 is equal to minus grad phi at 0, at gamma 0. Okay? I cannot really state this in this way, in this non-smooth setting, because I don't have gradients, and I don't have gamma prime. But there is a weak formulation of this, and this I can tell. Okay? So I'm moving along the direction given by minus the gradient of my Kantorovich potential. And why do I say so? Well, because now let's make this derivative. So we have a very nice measure, which is our evoluted measure along the heat flow, and our nice reference measure, which is nu. And now we have we want to differentiate the entropy along a certain geodesic, connecting our evolved measure to our reference measure. Now notice that this is a quite tricky business, right? To differentiate the entropy along a geodesic. It has to me it reminds the desire of differentiating the exponential map on a Riemannian manifold, right? You don't really know who is the differential of the exponential map. The best you can do is you can find an ODE satisfied by the gradient of the exponential map, which is the Jacobi equation. So because I mean you have curvature, so you don't know where you are when you do the exponential. You can only know. I mean, you know that you are sitting in here, use those small perturbations, and you see how this perturbation is sort of how the information is transported along the geodesic. And here we are sort of the same issue. We are sitting on a certain measure. We know that we are going to move in a certain direction given by the minus the gradient of the Kantorovich potential, but we cannot really know, I mean, what is the entropy at the end of the geodesic, because, I mean, who knows what happens in between. But maybe we know its derivative. Huh? That's sort of the idea. And indeed, this derivative we can compute. Why? So let me. So what do we do? So this is essentially the only computation that I want to show you today, and it's very important. So of course I pick the geodesic given by Rayala's theorem, and then I want to apply the metric Brownian theorem. So I start with the observation that the relative entropy is convex. I mean convex with respect to standard affine interpolation. So this convexity grants me a trivial inequality, which is the first inequality. So the first inequality, so imagine that nu s has some density, eta s m. So nu s is my geodesic. Okay. Then the entropy of nu s will be the integral of eta s log eta s, and the entropy of my regional measure would be, integral of eta 0 log eta 0. Now we have the, so I can write the following way. So u of eta s minus u of eta 0, right? Where u of z is z log z. Now for every point, I mean, u of b minus u of a is by convexity is greater or equal than u prime of a, so times b minus a. Right? I mean, this is true even without the integrals, right? So it's just the convexity of the function z log z. Now I apply this, I mean, divided by s, and what I'm obtaining is the first inequality. Okay, and then I take a ring sub. Okay, so easy. Now I rephrase the very same inequality using, rather than the measures nu s and nu0, my lifting pi. So that's the same as integrating the log of eta at time gamma s minus log of eta at time gamma 0 divided by s, integrated with respect to pi. That's the same, change of variable. Okay? And now here it is evident that, I mean, we are taking what I called yesterday an horizontal derivative. Right? So we have a nice function, which is log of eta, and we are differentiating in the direction of given by, I mean, curves in the support of pi. And we learned yesterday what is the result of this. And we know that this, I mean, if pi represents the gradient of a function, which it does, this derivative is what it should be in the smooth case. So it's grad of our functional times grad of the function whose gradient is being represented by pi. But there's a minus in front because pi is okay? So this is the crucial step. So we can take this derivative. Okay? We can differentiate in a certain, I mean, we can take directional derivatives. And now, from now on, it's just algebra, because this is computed just at the time gamma 0, but pi at time 0 is just eta. And now you have grad eta, grad log eta, that sort of simplifies out, right? And you remain with minus grad eta grad phi. But that's interesting because I mean that's precisely so. Let me go back one slide. So that's precisely so. Eta was I mean, now I apply this with my eta, which was my evolved measure along the heat flow. And this guy, you see that if you integrate by parts, is the same as the guy that we had in here. So I take eta as rho 0, right? I mean, you can integrate by part and get grad phi, grad rho 0 is the same. So these two derivatives are the same, and we deduce, I mean, with the same computation that we would have done in the smooth setting, that this derivative of the vastness distance is bounded by this difference of the entropy. So indeed, now by the arbitrarity of T0, the arbitrarity of nu, we've proved that our heat flow is a gradient flow in the EVI sense of the entropy, right? Which is false on general CDK infinity spaces. Actually, this is another characterization of our CDK infinity spaces. And among all others, there is one consequence that I want to underline, which is contractivity. So now if you have two heat flows, so two measures which are evolving along gradient flows of the entropy, then the Barstein distance at time t can be bounded by the Barstein distance at time 0 times an exponential factor. How do you prove this? Well, imagine the case k equals 0, just for simplicity. And now write the first inequality and at time t, where as reference measure you pick nu t. Okay? And now write the first inequality for the evolution nu t, where you take nu t as the reference measure. So you would obtain, I mean, sort of two very similar inequalities with the right-hand side, two things which are swapped. Now you add those inequalities, and you obtain that the sum of these two derivatives is less or equal than 0. And now it is just a matter of Gromoll, and you deduce the contractivity. Okay? And again, contractivity is false on CDK infinity space. There are explicit counterexamples given by Ott and Sturm. Very well. So we have a heat flow, which is contractive. And by the way, the fact that the contractivity also allows us to start the heat flow from a delta. A priori, we were not able on CDK infinity spaces because we need to start from measures in the domain of the entropy and whatsoever. But as soon as we have this contractivity property, what do we do if we want to start from a delta? Well, I just pick a sequence of measures for which I know how to start the heat flow, which are weakly converging to my delta. I mean, and now these flows will converge somewhere thanks to this contraction property. Okay? So I have a heat kernel. And if you have the heat kernel, which, by the way, let me also emphasize that heat kernel, if the heat flow is not linear, is really a meaningless concept, right? I mean, if you don't have a linear heat flow, you may know how to start a flow from a delta, from another delta, and then you say was the heat flow starting from the sum of the two deltas, and that may be totally unrelated, right? I mean, because it's not linear. But once it is linear, you have and you have a heat kernel, then actually you can apply all the more or less standard machinery of the Dirichlet forms to get for free the existence of a Brownian motion in the spaces with continuous sample paths. So you just declare a Brownian motion. What it is something whose sampling at time t is given by the heat kernel starting from that at your point. And then you want the increments to be independent, and that's all. Okay. And the fact that your Dirichlet form is local grants you continuity. Okay. And I don't want to spend too much time on that, because that's, I mean, you can more or less apply as a black box known stuff about the Dirichlet form to get the results. So let's focus on things which are proper to lower Ricci bound. Let's speak about Bochner inequality. So Bochner inequality, now I'm not sure if we have already sort of discussed this in this. Did we? Not yet. It's time, right? I mean, we cannot speak 3 days of lower Ricci bound without ever mentioning Bochner inequality. That's sort of the inequality of geometric analysis, and the inequality which characterizes lower Ricci bounds. I mean, that's sort of important. In the smooth setting, Bochner inequality is the following. I mean, there are various versions, but I propose you, I mean, the one that I will deal with. So Bochner inequality tells you that you have a smooth function over a smooth. Yes. Just yeah, yeah. Oh, okay. No, I just read inequality. I really want inequality. I mean, because the equality will take time to be written. So let me just write. I mean, the osmo setting. Let me just write the inequality. So let me just write it. So pick a smooth manifold, pick a smooth function, and ask if this is true. And if the answer is yes for every function, then your manifold has Ricci curvature bounded from below by k. And that's an if and vice versa. If the Ricci curvature bounded from below by k, then you have this. Okay. And if you so without anything about, I mean, I'm not imposing any upper bound on the dimension. If you want an upper bound on the dimension, then you can add here Laplacian squared over n, and now this is true if and only if your manifold has dimension less or equal than n, and Ricci curvature greater or equal than k. Okay, but for the moment, I mean, on the infinite dimensional case, so let me forget about this. Let me try to see. So this inequality characterizes manifolds with curvature bounded from Ricci curvature bounded from below by k. Now I have metric measure spaces with Ricci curvature bounded from below by k, so I may wonder whether this is true as well. And of course, the problem is that here there are quite many derivatives, right? I mean, and to deal with in non-smooth setting. So how do we do? And here is the point. So there is a beautiful lemma, a beautiful duality result due to Cuvada, which I'm not going really to honor by the way it is written, but let me sort of, let me state in this form. So you have. Suppose you have a linear heat flow. So we have a metric space, say, and we have a linear heat flow at the level of measures, and with the capital H, while small h, I mean, is the same flow at the level of densities. It's just, I mean, I just want to distinguish the two objects. Well, then the following are equivalent. That's a very nice duality result due to Cuvada. First, you can control the squared Warzmann distance between two evolved measures with the distance at the initial time times some factor for every couple of measures and every time. And that's equivalent to controlling the local Lipschitz constant of the evolved density with the local Lipschitz constant of the initial density. Evolution of the local Lipschitz constant. So the local Lipschitz constant we have already seen is this object. These two are equivalent. So for every LP. Cuvada did this duality on metric spaces for every P, Q, etc., etc., and Sure, but this is metric setting, and I mean, that's an important point. I mean, that's an important point. The important point is that you can derive this Bakri-Emery estimate out of a Wasserstein contraction in the non-smooth setting, in a place where regularity is an issue, because you don't know what regular functions are. Okay? So and then there is this nice argument of Kuvada, which of course is based on known stuff. That's more recent, and that's true. I agree. And with Edbar and Sturm also, they did something in this direction, and they characterized, I mean, finite dimensional, I mean, RCD-KN spaces via Bochner inequality. But yeah. But what I want to emphasize here is that in the genuine non-smooth setting, a purely metric property like the Wasserstein contraction controls, I mean, it's equivalent to another purely metric property, which is the this contraction of the local Lipschitz constant. Okay. Why do I emphasize this? Well, first of all, let me restate. I mean, let me sort of. I like this inequality up to a certain point because I stated that I like to do analysis with Sobolev functions, and here I have Lipschitz functions. So I would like to translate this information in a Sobolev information, which is sort of more easily manipulable from the analysis point of view. So how do I pass from a Lipschitz information to a Sobolev one? Well, I use the following result concerning density in energy of Lipschitz functions in the Sobolev space, which is in fact something which I already implicitly stated when I was saying that our initial energy was the relaxation of the integral of local Lipschitz constant squared. So the theorem here is that whenever you have a generic metric measure space, well, you have this. Well, the first lower semi-continuity property of this minimal weak upper gradients is something that we have already seen. So if you have a Lipschitz function, then its local Lipschitz constant is an upper gradient. You can use it in the definition of Sobolev function. So thanks to the general lower semi-continuity property of weak upper gradients, if the sequence of functions local Lipschitz constant admit any weak limit in a 2, then G, say, then your limit function is Sobolev, and this G is an upper bound for the minimal weak upper gradient. Okay? So that's a lower semi-continuity result which is already stated. I mean, it's a consequence of what we've already seen. What is non-trivial is that for every Sobolev function, you can find a sequence of Lipschitz functions converging in a 2 to F, such that their local Lipschitz constant strongly converge in a 2 to the minimal weak upper gradient. So it's a density in energy. Okay? So this is true. And why, I mean, why this is relevant to our discussion? Because now look at that. So on our RCD K-infinity spaces, we had Wasserstein contraction. So thanks to Kuvada, we have for any given Lipschitz function, we have this inequality, which is a very Bakri-Emery-like sort of inequality. But now I want to state the same inequality for Sobolev functions, and that's pretty easy by relaxation, because take your preferred Sobolev function f, approximate it with fn in the strong sense, and now the right-hand side will converge. Now ht of fn will converge to ht of f. Maybe it won't be optimal, but anyway, the inequality goes in the right direction. So this left-hand side is less or equal than the limit of the left-hand side above, which is less or equal than that, which is equal to the limit here. Okay? So you get the Sobolev information in here. And now with this we are very happy, because in the smooth setting, this inequality is equivalent to this inequality without the equivalent. How do you do in the smooth setting? Well, imagine k equals 0 just for simplicity and differentiate. At t equals 0, you have equality. You have df squared equal df squared. So for any other time, you have an inequality, so you can differentiate, and the derivative, I mean, at time 0, I mean, passes, I mean, as the same inequality. Now, if you differentiate at time 0, the left-hand side, you get twice this guy. Right? If you differentiate at time 0, the right-hand side, and say k is equal to 0, you get twice this. So you get this inequality over here. And in fact, I mean, you can prove that there's a nice trick due to Bakri and Devery that if this holds, then you have that inequality in the smooth setting. But the point is that now we can formulate this inequality even in a non-smooth one, How do we do to be sure that everything is well posed? Well, we multiply by a function g, which has a positive, and that's a Laplacian, and now take the derivative. And what you come out with is that the integral of Laplacian g grad f squared over 2 is bounded from below by, this quantity multiplied by g and integrated. And yeah? Sorry? Yes. Yes, this is Herbart-Cuvada-Sturm. So even in the finite dimensions, so they've been able to, you have to modify to find a way of, fixing coefficients and so on, but then they can put. Okay. So this strategy was proposed in, with Cuvada and Dotta, we proved the Bochner inequality in the Alexandrov setting, and then with Ambrosio and Savary, we realized that, the Alexandrov assumption was not really needed. The Ricci assumption was important, and we got the Bochner inequality. And it is important to underline that. So I can write this inequality only, for those functions which are regular enough for this inequality to be written. So what do I want from f? From f, I want that to be Sobolev, to have a Laplacian, and the Laplacian also should be Sobolev in order to be able to write this. But there are plenty of those functions. Take your preferred function in L2, apply the little bit of heat flow, you're done. And what do I want from G? I want it to be bounded, because I'm using it, and I want to have a Laplacian with bounded Laplacian and non-negative. And this is also easy. Essentially, start from a bounded positive function G, apply a little bit of heat flow, take some average, and you're done. Okay? So there are plenty of functions for which this is true. Okay? And actually, it is worth now to underline that you can also go backward in some sense. So if you pay a lot of attention to technical issues, you can start from a metric measure space for which you have a big enough class of functions for which this inequality is stateable and is true, and then you can actually check that your metric measure space was RCD. So from this differential inequality, you can go back up to the K-convexity of the entropy and infinitesimal libertarianity of the space. That's very technical, and I will not give details in that direction. Sorry. Also, so with any infinity is the hard issue. Because once the hard issue is to provide a link between Sobolev calculus and metric information. Once you have this, you are in a solid situation in which from a Sobolev information you can derive a metric one, and now this already gives you quite a strong regularity of your metric measure space, which a priori was not needed. And now you must say, okay, suppose that I know that my Bochner inequality was not valid just for these guys, but with n, and can I improve that up to an RCD, Kn, whatever? And the answer is yes. Okay. Yeah, plus quite a lot of technical issues.
Sure, but it's not like Bochner implies
Bochner requires infinitesimal libertarianity to be written.
Really?
Yes. Not, but yes. So, okay, you don't need the linearity of the Laplacian.
Just if I read this, it makes sense to me that W12 is a balance space.
True, absolutely. I totally agree. But the point is, so let me write this. So pick a Finsler manifold and try to write down Bochner inequality for that. You can, but the Bochner inequality written as Laplacian grad f squared greater or equal, that is false. That is not the way of writing Bochner inequality. No. So what I'm saying is that this makes sense even in a Finsler setting, right? But in the Finsler setting, does not characterize lower Ricci bound. So, no, absolutely no. That's. Although actually, I don't know of any single example where this holds, and the Laplacian is not linear. Now I'm in trouble. So maybe it does. I don't know. I don't know. So, but the correct way of writing Bochner in the Finsler, the way that it characterizes. So here you should take the linearization of the Laplacian in the direction of grad f. So now you still have a sort of quadratic object, and this is this is differential of this applied to the gradient of f. Look, you don't want to. I mean, trust me. You don't. No, especially in the non-smooth setting. I mean, it's on metric measure spaces that there are, I mean, even other technical issues that need to be addressed. Well, now, I mean, this is finite dimensional. So all this program can be also, I mean, works even if you add the finite dimensional term in here, and so you have full equivalence between the Bochner inequality written in this way and the RCD star Kn condition, which I've never written, and so I'm lazy to take RCD plus this inequality as definition of RCD star, if you wish. Please. Yes. Yes. So they start from these well, actually, so they start from certain convexity, improved convexity property of the relative entropy, which they prove to be equivalent to the geodesic convexity CDKN implicit in the CDKN notion. From this improved geodesic convexity, they get an improved Wasserstein contraction. This improved Wasserstein contraction gives you improved Bakry-Emery, and this improved Bakry-Emery gives this. And the fact that in the end of the game you get the Bochner inequality tells you that all these improvements were sharp, because you obtained the sharp lower bound on the Ricci, right, in this node case. Okay, so the strategy is that. Yeah. Okay. And there's also another work in progress by Ambrosi, Mondino, and Savare, where, I mean, okay, so Abresch-Gromoll and Sturm, they got this nice idea of studying, I mean, continue studying just the entropy functional, even in the finite dimensional case, while Ambrosi, Mondino, and Savare studied the so-called Renyi type entropy functional. So this is something like minus the interval of rho to 1 minus 1 over n. So which is a less linear version of the relative entropy, and apparently studying just the Boltzmann entropy is technically way easier. I mean Abresch-Gromoll and Sturm, they got a quite clean result in not that much of time. Yes.
So does this mean that you can now study the heat flow with this problem?
Sorry, you can. That even in infinite dimension you can. You have an it kernel even in RCD K infinity spaces because of the contractivity. You can start from absolutely continuous measures with finite density, with bounded density, and now approximate a delta with those, and use the contractivity to get a limit. What? So it was no even for infinite dimensions, so in particular also for finite. So this set of spaces is included in RCD in K infinity, right? I mean, you can throw out this term and get, I mean, an even better inequality. So all what was known on RCD K infinity was known also here. Did I convince you?
Yeah, it's interesting that the infinity case is just first, and then the finite case. This is 13 where
you want to prove more in some sense. So it requires more. And moreover, you want to start, I mean, philosophically, you want to start from RCD K infinity because whatever you prove there is true everywhere, right? So it gives you a solid ground where then to work in the finite dimension. Now, let me also emphasize that, I mean, this Bochner inequality has a number of consequences in the smooth case, which now more or less, I mean, now let me cheat a bit. I mean, from Bochner inequality and algebraic manipulation, you can prove a lot of other interesting inequalities in this whole setting. Now we have the Bochner inequality in non-smooth one, so you can try to see if the same algebraic manipulation gives you the same result. Of course, in doing this, you will encounter some technical issues here and there, so it's not so easy. But there are quite a number of regularity informations that come for free, or more or less for free, once you have the Bochner inequality. And here are a couple of ones. So Mondino and Garofalo proved the Lie inequality. So pick the heat flow starting from a non-negative function, evaluate the time t, and take the log, take the Laplacian, and if your initial space had non-negative Ricci curvature, this Laplacian is bounded from above by minus n over 2t. That's a magic inequality. It's scale invariant. Multiply by 100 your initial datum, well, doesn't matter, because anyway you take the log and then the grad, and so that constant disappears, and you still, this is totally uniform bound from above the Laplacian, which is sharp, because for the Gaussian Rn it is sharp. And moreover, harmonic functions are known to be locally Lipschitz on Riemannian manifolds, and with constants which only depend on the lower Ricci and upper curvature bound. And the proof essentially is Bochner inequality plus elliptic regularity theory, which is in turn based on doubling and Poincare properties. Now, all of this stuff is known to hold on RCD Kn spaces, so these proofs can be taken and obtained in even non-smooth case. And there are a number of results in this direction. Okay. Bootstrapping, no, it's not enough. No. Let me tell you one word. I mean, I will not prove anything in here, but I want to mention one result concerning optimal maps has been obtained by myself, Rayal and Sturm, which concerns essentially Brownian-McCann theorem holds with more or less the same assumption and the same thesis, even in this RCD Kn setting. So RCD star Kn is RCD K infinity plus Bochner inequality with the n. That's our working definition for RCD star. And the point is that now take two probability measures and assume that the first is absolutely continuous with respect to your given volume measure. Well, then there is only one optimal plan for the Weierstein 2 problem. The plan is induced by a map. For almost every point x, there is only one geodesic starting from x and going to t of x. So this optimal map never encounters, or almost never encounters, the cut locus in some sense. And moreover, the space is non-branching along this direction. So for every x and y different, and every t between 0 and 1, those two geodesics going from x, y to their image never overlap. Okay, so that's really the same as McCann. I mean, more or less the same sort of information that we deduced from McCann theorem in a non-smooth setting. The proof is quite involved and long. I mean, I won't give detail. Essentially, in this setting, I'm afraid so. On McCann, no, right? You can sort of do a little bit less, but I mean, do not charge n-1 rectifiable sets and whatever. But here, I mean, I don't know. What did you mean by? I mean, I would not really have any idea on how. I mean, yeah. Even because here, as you know, there are issues between the geometric dimension, the analytic dimension. So what is n-1 if I am allowed to take n bigger than my true dimensions? I wouldn't know how, not even how to state results sharper than this, to be honest. Okay. But the proof is quite complicated. So the point is that Rayal and Sturm proved that once you are on an RCD K infinity space, well, I don't have time. So it's long. I mean, it builds up several papers. Daneri Savare, Rayal Sturm, myself, Rayal Sturm. I mean, it's quite long, but it's good to know that we have a McCann version. Now, I want to spend a couple of words on the distributional Laplacian, because now that we can integrate by parts, we can speak about distributional Laplacian. So let me give you the definition. So let's say that forget about RCD and take an infinitesimal Hilbertian space. Take an open set, say that the space is locally compact for simplicity, and take a Sobolev function on that open set. Now, I can say that this function has a measured value of the Laplacian, provided there is a measure mu, a Radon measure mu, such that for every Lipschitz function with compact support in omega, the integration by part rule holds. This makes sense. It is a definition, right? The left-hand side is what we defined with this limit of minimum weak upper limit of G plus epsilon F squared, right? Minus grad G squared over 2 epsilon. So it is something which is well defined. And I might wonder whether this is true. Okay? And so this is a definition. And well, in this case, it's easy to check that mu must be unique if it exists. I mean, because Lipschitz functions are dancing continuous functions. And I call it Laplacian of G restricted to omega. And some basic calculus properties. Now, given that I worked I chose to work in infinitesimally Burtian spaces, this Laplacian is linear. I could give the same definition on more general metric measure space, and the Laplacian won't be linear in general. Linear, of course, means that I forgot alpha 1 and alpha 2 on the right-hand side. I guess you can guess that. And then you have a natural chain rule and Leibniz rule. So these are all true. And they are true. I'm not stating all the regularity information, the regularity assumptions behind, because much like in the smooth setting, every time these formulas make sense, it is true. So here I might be in trouble because I multiply a measure by a Sobolev function. So in general, I don't really know. But whenever this makes sense, then the formula is true. So says G is continuous, for instance, and so on. Okay, now what do we do with this Laplacian? Well, first of all, we can characterize subharmonic functions. So there is a research field in analyzing metric spaces, which called nonlinear potential theory, whose target is to study the behavior of harmonic or subharmonic functions on metric measure spaces, which you can define even if you don't have a Laplacian, right? You can say that an harmonic function is a function which minimizes the Dirichlet integral among all perturbations with compact support within your open set, right? Or within your compact support with a certain sign on your open set. And now we have a Laplacian, and we can wonder whether there is any relation between the sign of this Laplacian and the property of being harmonic or subharmonic. And the answer is yes, because as soon as your space, says infinitesimally Burtian and satisfies a doubling measure and supports a two-Poincare inequality, which by the way is always true in RCD star Kn spaces, then you have the same characterization, a PD characterization of subharmonicity, perfectly equivalent to the one available in the smooth setting. So your function minimizes the energy among all perturbations with positive functions, if and only if its Laplacian is negative. If and only, like on RD. So in particular, it's harmonic, if and only if the Laplacian is 0, like on RD. So this provides a PD characterization of minimizer, which was missing. I mean, this subject. So studying this sort of minimizer is a topic which is, is known, I would say 10 years at least in metric measure setting, or even more. But a PD characterization was missing, and now there is. And moreover, yeah, please. Local, weak local Poincare inequality, yes. Well, yeah, forget about the sign of f and the sign of the Laplacian. So let's take this. Laplacian of G is 0 if and only if for every f with support inside omega this is true. So Laplacian equals 0 characterized minimizes of the Dirichlet energy. Now if you prescribe a sign on a perturbation, you get a sign on the Laplacian, right? If you look like a parabola, let's say a parabola like that, you are minimizing the energy among all functions bigger than you, and your Laplacian is negative. So that's precisely that. You write the Euler Lagrange equation of this guy, and you put that. Say it again. So these are the definitions of subsolution and supersolution. And you characterize them via a PD. This is the definition. Okay. Okay. Now there's one more thing that I want to point out, which is Laplacian comparison estimates. So take a smooth manifold with, say, non-negative Ricci. The things can be adapted with Ricci bounded from below by generic K, but let's say non-negative. And dimension, let's say, equal to n. then what you know, I mean, this is a classical inequality in comparison geometry, is that the Laplacian of the 1/2 distance squared from a given point is less or equal than n. Now, in a smooth setting, we need to understand what this means, because as far as the distance square function is smooth, then, I mean, that's a standard Laplacian, but distance can be non-smooth, even in a smooth manifold. You can have corner, right? But the point is that all corners that the distance function can have on a Riemannian manifold are concave corners. So in fact, this inequality is true, if you wish, in every sense. It's a global inequality. This is true in the sense of distributions, in the sense of viscosity, in the sense of barriers, in whatever sense you can write this inequality in order sort of to deal even with possible singularities of the distance function. The inequality is true. Okay? So we can wonder if the same inequality is true even in non-smooth setting. And out of all the possibility, we have only, I mean, up to now, we have only just one definition, which is the definition of distributional Laplacian, and we can wonder whether the same is true, even in a non-smooth setting, and it does. So RCD star n, so the Laplacian of the square distance, 1/2 square distance, is bounded from above by n, in the sense of distribution. Please. It's a chain rule. By the chain rule, the Laplacian of, the way typically the Laplacian comparison estimate is written on the Riemannian manifold is Laplacian of, yeah, so this is less or equal than what is n minus 1 over d on m minus, right, the singleton, right? And that's the same, I mean, the same is true, the distributional sense, in the open set, all your space minus a point, you get this inequality. So no, it's not Finsler. So this inequality actually, I'm stating and writing it for RCD, but actually it's true for more general CD Kn spaces, even Finsler. If you take RCD Kn with a bound K, then indeed on the right-hand side you have some arc cotangent of some bizarre function of K and distance, etc., etc. But it appears some trigonometric function. Okay. No, it's not Finsler. It's nothing to do with Finsler. It has to do with a lower Ricci bound with a K which is not 0. And the inequality, so the Laplacian comparison estimates are as valid in the Finsler setting as they are in the Riemannian setting. Okay, and even actually in the sort of non-smooth Finsler, so CD Kn. Okay. Let me give 2 words on the proof. How do we prove it? Well, that's the very same, sort of very similar computation that we did in differentiating the entropy along a geodesic. The idea is, fix your preferred non-negative function, f Lipschitz with compact support, and define a probability density by sort of taking a proper power of f and multiply it by the normalizing constant. And consider the geodesic connecting your measure with density, the one that you built, to the delta in your point from which you are computing the distance. This doesn't exist and is unique, right? Because of the result with Rayal and Sturm. Now, this functional un is the functional, so un, I never really introduced it, so let me do it now. So un of rho m, that's minus the integral of rho to the power 1 minus 1 over n. And it is a fact that this functional is geodesically convex in the Wassner space whenever you are on a CD0 in space. That's sort of by definition. Of course, I'm cheating now because I'm speaking this by definition, and previously I said that the definition was Bochner inequality, but in fact the two are equivalent thanks to Herbert quadrant. Okay? So we have the geodesic convexity of this guy. And now, if you apply this geodesic convexity, you compute now the sort of the limit of the incremental ratio. The geodesic convexity tells you that the incremental ratio is bounded by the difference of the function at the extrema. But now, sort of this guy as 0. I mean, this function computed in the delta is 0 because delta has no density. So it is 0 now, and you rest just with minus un of mu 0, which is this. So you have here it appears your initial Lipschitz function, and which was normalized this way. And so this is the trivial inequality. The slightly harder inequality to bound from below this incremental ratio. We do the very same inequality, the very same trick that we did in differentiating the entropy. So the first step is I use the convexity of the function, which takes a real number a and gives back minus a to the power 1 minus 1 over n to get the very first inequality. Then I use I pass the integration to the level of pi, which is the lifting of the geodesic. And now pi represents minus the gradient of the Kantorovich potential, which is the distance squared over 2. So I do the very same computation as before and I obtain this. So it's just, I mean, if you're able to do this directional derivative, and you do that, you obtain this point, that the integral of f dm is greater or equal than this integral for every f greater or equal than 0 with compact support. And now you can realize that this inequality, in fact, is telling you that the Laplacian of this guy is bounded from above by n. Imagine you integrate by parts, and you multiply by n, and then you are done, right? Because that's true for every Lipschitz function with compact support. Okay, so that's the way. I didn't finish. So that's the way. So you prove a Laplacian comparison. No, I should have just 5 minutes if I'm right. So let me just point out a couple of things about how to use these informations about Laplacian comparison and other differential calculus. Because so far I've just sort of played with analytic tools, and I didn't seriously give you any geometric reason for believing that RCD over CD should be a better notion. So now let me try to convince you with a few theorems concerning the shape of the function. So how this Sobolev information governs really the shape, the geometry of the spaces. Now today I will just show you the Abresch-Gromoll inequality. Tomorrow we'll speak about a splitting theorem and maybe mention some result, one of Christian Ketterer, who is here, and other by Mondino and Haber concerning rectifiability. But let me just spend a couple of words about the Abresch-Gromoll inequality. So what does the Abresch-Gromoll inequality tell us? It is an inequality which is valid on Riemannian manifold with a lower Ricci bound and upper dimension bound, and it tells something about the shape of thin triangles. So the idea behind the inequality is this. Imagine you are on a geodesic space, and you take a geodesic, and you take a point which you should imagine not in the geodesic and close to the midpoint of the geodesic, but far from the extrema. Now, define the function h, h of x. That's the minimal distance, so the height of an imaginary triangle which you are drawing in here. So h of x is the inf of the distance between x and gamma t. Okay, the inf over all t is where the gamma is defined. And define the function e, the excess function, which is how much you fail the triangular inequality. So it is the distance. So e of x is the distance between x and gamma 0 plus the distance between x and gamma 1 minus the distance between gamma 0 and gamma 1. Okay? Now, of course, if h is 0, then you are sitting on the geodesic, and therefore e is 0. Okay? Now, suppose you want to bound e in terms of h where you are not 0. If you are on a generic metric space, the best you can do is to apply triangular inequality and tell that e is less than twice h. And in the metric space, this is realized. Then if you take say an L infinity, a flat norm or whatever, then you really have equality. On the other hand, if you are on the Euclidean setting and you are interested in the regime when h is small, then by Pythagoras, you know that e goes like h squared. Right? Because this length is something like square root of, say, half of this guy plus h squared, but square root of 1 plus h squared is of the order 1 plus h squared. So it goes like h squared. And now what Abresch and Gromoll tell is that if you only have a lower Ricci bound and an upper dimension bound, then indeed you can bound the excess in terms of the height with a function which is more than quadratic. sorry, it's more than linear. So it goes to 0 faster than x. Okay. So this, this function is explicitly given in terms of k and n. It degenerates when n goes to infinity. This becomes more and more linear. So when n is infinity, you don't really get nothing. But you get a quantitative bound on how the x's can be bounded by the height. Now, of course, you can wonder whether this is true on CDKN. And on CDKN spaces, this is false. Because CDKN spaces contain Spinster structure. You pick Rn with the Lebesgue measure and the L infinity norm, and this is a counterexample to the Abresch-Gromoll inequality in the normal setting. Okay? And this was a criticism to the definition of CDKN, coming from geometers and said, look, this inequality, by the way, notice that this inequality, given that f is explicitly given, it is automatically true in Ricci limit spaces. Whatever space you can obtain as limit or Riemannian manifold with a certain lower Ricci and upper dimension bound satisfies this inequality because it is satisfied in the approximity space. Okay? But on Fisher spaces, this is not true. And then you say, what's going on? And let's try to prove this inequality in an osmose setting, and in some moment we will get stuck, and we will see what we should do in order to modify the definition. So you open the paper by Abresch and Gromoll, and you check what are the ingredients of the proof, and there are 3 ingredients. This Laplacian comparison of the distance, the linearity of the Laplacian, and the weak maximum principle. So essentially, the proof of this inequality is based on the fact that you take the Laplacian of essentially of the x's function, so of the sum of the distance from x and the endpoint and x and the other endpoint. Okay, and then you apply some weak maximum principle, and you have a Laplacian comparison estimate, and you apply some weak maximum principle. Now the weak maximum principle is true in basically every metric measure space in some sense. It's really a very weak requirement. I'm done. The Laplacian comparison is true on every CDK infinity, but the linearity of the Laplacian, for that you really need the R. That is really the same as requiring W12 to be Hilbert. So what you can do is you pick the paper by Abresch-Gromoll, you change manifold M with the space X and RCD, and you change the names in front, and you got the Abresch-Gromoll inequality in the RCD. So that's a very concrete proof, and was also the first one given of a concrete geometric consequence coming out from this abstract Sobolev calculus. So you say, what do you do with Sobolev calculus? Well, you prove that triangles behave like they should. Okay? And tomorrow we'll continue with the splitting and etc. Thank you.
Any questions? Yeah? So
Sorry, if I? Yes.
Can you compare, if you're like these famous Riemannian geometry comparison theorems on fundamental solutions between like your space and your model space, so you have like 3 different. Can you obtain similar things?
Well, so I'm not sure which results you're referring to. So Li-Yao, so these I don't know. So yeah, so no, I was saying Li-Yao are true, as I mentioned. Shigeru-Yao, I don't know this, and so I don't know if they are. It would be a kind of. So typically, whatever concerns the heat equation, given that the heat equation is the object that you use to define those RCD spaces, and it is so well behaved, typically they can be transported quite easily to the non-smooth setting. But I cannot make I don't know these results specifically, so maybe. No. So wait a moment. That was on just doubling and Poincaré, right? So then you have Arnack inequalities and these sort of things. But this sits. Sorry. Yes, L infinity bounds and the Gaussian estimates and so on and so forth. But these do not rely on lower Ricci bound. Rely on something much weaker, which is doubling and Poincaré. Okay. So. So those bounds, by Sturm that I know they're really based on something else, so doubling and Poincaré, which is weaker than rho Ricci. So you cannot get the same bounds that he's looking for. So take RD, take Euclidean distance, and take as measure whatever measure which is between Lebesgue and twice Lebesgue. That satisfies doubling and Poincaré, but it can fail a lot in having lower Ricci bound. So the bounds by Sturm will be true, but no bounds like those wanted in